Welcome to today's presentation. We are excited to share with you our research on optimization of data protection in IoT field of cloud computing use compiler privacy calculation method. This study focuses on enhanced data security in the Internet of Things, the IoT domain within cloud computing, utilizing a novel compiler privacy calculation approach. Allow us to introduce ourselves as the author of this paper. I'm Huang Xingcheng and my co-author is Huang Jingjia. Together, we have embarked on this journey to explore innovative solutions to bolster data protection in the rapidly evolving world of IoT and cloud computing. Throughout this presentation, we will walk you through our findings, methodologies, and the significance of our proposed approach. We hope you find our research both informative and inspiring. And this is our contents. There's 6 parts. And the first is the introduction. Due to the uncertain security of cloud computing virtual environment and insecure factors such as data hijacking, data needs to be encrypted before being uploaded to the cloud. Aiming at the protection of data in cloud computing, this paper proposes an optimization of cloud data protection based on the compiler privacy computing method. Consider the cases of code generation and programming challenges. We choose to use the Porcupine compiler to make homomorphic encryption code automatically generated. And the second part is the background. First is the elimination of study. A noteworthy constraint of the current research relates Tony's encryption technique, which relies on a blend of homomorphic and symmetric encryption. Homomorphic encryption's chief drawback is its costliness. Another bottleneck of the research is the compiler, specifically Porcupine. However, Porcupine cannot guarantee accurate recognition of all inputs. To counter this, we utilize Query to interpret the semantics of homomorphic encryption program's behavior and enable the compiler to detect potential optimizations changes to discrete manually. And pertinent literature as a magnitude of encrypted data on cloud service escalate, the retrieval of such data presents an increasingly urgent challenge. Yun Hong's team put forth and realized the design and execution of the sector storage cloud and the spherical computing cloud. Their research showed that the sector speed was approximately twice that of stop, indicating significant efficiency enhancement. Li Kun Liu of Tsinghua University designed and actualized the Zeta data storage system that conserves resource by operating on a non-dedicated system. The system effectively utilizes storage space when handling a plethora of small files, achieving superior transmission performance. And I will introduce two encryption types. One is homomorphic encryption and one is asymmetric key algorithm. The homomorphic encryption allows performance mathematical operations on encrypted data without the need to decrypt it first. This ensures secure computation while preserving data privacy, making it ideal for applications like cloud computing and data sharing. And to the asymmetric key algorithms, it uses the same security key for both encryption and decryption. It's fast and efficient for encrypting large amounts of data, but requires careful key management to maintain security. Now it's the ProCompile and QCompiler and machine learning. However, homomorphic cryptography is limited by programming challenges and excessive overhead. Therefore, ProCompile and QCompilers were used to solve this problem, while the ProCompile compiler can convert the input information directly to the output ciphertext. Quill captures the same semantic of homomorphic encryption instructions and use ProCompile to convert the input information to the output ciphertext. Machine learning system learns from data and patterns to make predictions, identify patterns, or make decisions. This data-driven approach allows machines to adapt and improve their performance over time, making them valuable tools in various fields such as image recognition, natural language processing, recommendation system, and more. And the third part is the method. There's 8 steps. First is I need to introduce the method. Overview of the assignment study, which focus on the development of a compiler assistance symmetric key homomorphic encryption scheme for matrix operations. This strategy utilizes the ProCompile optimization compiler and domain-specific languages named Quill to compile efficient kernels. An advanced synthesis process is used to create a hardware accelerator for homomorphic encryption that performs Kara's supermodular polynomial multiplication and is a compiler assist encryption. The tool compares the actual description of compiler assisted encryptions. This technique takes encrypted functions code from the programmer and determines suitable encryption for each data item in the function code. Different encryption primitives are applied to data items based on their operations. The use of cryptography homomorphic encryption during arithmetic operations and for symmetric key encryptions when data is stored without operations, and the role of Porcupine compiler and QDSL. Details about the auto-generation of code through program synthesis by Porcupine compiler and QDSL to tackle three major compilation challenges. Discussion about the benchmarking test of Porcupine synthesis. Explanation of the implication for users. They can focus on current coding without worrying about performance adjustment, and the query program and its metadata. Explanation of the state of the query program defined by vectors and words with the highest values. Overview of metadata associated with query, including depth tracking data of each action and simulation prefix. Description of how query handles conditional statements or loops and boundary combinations using simple instructions. And the following four steps is Porcupine search for optimized solutions. Description of process of using Porcupine to find an optimized solution to the kernel specification. Explanation of Porcupine's reciprocal of the inclusion and the induction synthesis period. Discussion on the role of ROSET's built-in support for SMT phrasing in converting unified and validated queries into constraints. And step in the method is discussion on the inquiry and code generation steps involved in the method. An explanation to of how Porcupine completes the sketch of the program using components and how the synthesis engine generates homomorphic encryption kernels. Details about the role of Q and Porcupine in converting Q code into C code, and the further steps in the method. Discussion on the post-processing steps that need to be completed before the code can be generated. Explanation of the synthesis formula optimizations process undertaken by Porcupine to handle a large kernel, and the last is the kernel specification. Overview of the kernel specification, which completely describes the functional behavior of the target kernel. Details about what the synthesis kernel needs to calculate, as defined by the kernel specification. Having discussed the methodology in depth, I now pass the baton to my co-author Huang Jinjia. She will lead us through the enlightening discussion, exploring the implications and potential Applications of our research in optimizing data protection in the IoT field of cloud computing use the compiler privacy correlation method. Let's continue this journey together and gain valuable insights into our findings.
Thank you for the previous presenter for delivering such insightful content. In the discussion section, we will further explore the findings presented earlier and brighten them with our analysis. In the discussion section, we will compare homomorphic encryption with other encryption methods, analyze the advantage and disadvantage of homomorphic encryption, and optimize the compiler with algorithms. Next, we will showcase the evaluation results equipped using CKKS and BFA. Homomorphic encryption schemes, comparing them with the comprehensive evaluation results obtained through direct plaintext weighted average. These results will further support our analysis of advantage of homomorphic encryption. From figure above, we found that BFA is better than AES in terms of encryption time, decryption time, and security. This is the main reason why we use homomorphic encryption algorithm to protect computer and cloud computing. Although HE is already an excellent algorithm, its plaintext field is integer vector, so it cannot handle the problem of floating point numbers. To solve this problem, we found a solution. Develop a new homomorphic encryption system, CKKS, based on the BFA. Compared with BFA, CKKS has the greatest advantage of being able to handle floating point numbers, even complex number. The plaintext field of CKKS is a complex vector. In fact, CKKS construct based on BFA. During the paper completion, we encouraged several limitations. We were unable to access experimental proofs, resulting in the use of second-hand data from literature and books to compare homomorphic encryption with other algorithms and analyze Porcupine compiler advantages. Additionally, time and technology constraints prevent us from developing more code from proposed optimizing. Furthermore, we observed that CKK system drawback lies in its time-consuming nature compared to the BFM system. In the future, we hope for emergence of an encryption algorithm that combines the advantage of time saving in traditional homomorphic encryption system while efficiently handle complex vector, similar to CKK's system. This paper describes how data servers encryption and privacy protect data in cloud computing, comparing the advantage and disadvantage of homomorphic encryption with other data encryption methods. We introduced a compiler model, Porcupine, and a Qlin, which automatically generate homomorphic encryption code that is similar, faster, and better than realizing the potential of homomorphic encryption than traditional hand encryption method. Based on our research, the quest of explore compilers that implement homomorphic encryption faster with better performance and cheaper remains a great challenge for humanity in computing decades. As we approach to conclusion of our presentation, I want to take a moment to acknowledge the number of the reference and research materials that have enriched our contents and informed our perspective. Their contributions have been instrumental in shaping the insights we have shared today. Lastly, we extend our heartfelt gratitude to all individuals and institutions whose support, guidance, and contribution made our presentation possible. Your encouragement and expertise has been invaluable in shaping our work. Thank you for being a part of the journey with us. Thank you.